Hi everyone, my name is Adji Bousso Dieng. I am a PhD in the statistics department at Columbia University, where I work with David Bly and John Paisley on combining ideas from probabilistic modeling and deep learning to build expressive models for data, and then expressive model for data, but also devising variational methods to learn with these models. Today, I'll talk about structured deep generative models. These are a family of models that account for structure in data. And the reason why we might be interested in this types of model is that a lot of the data that we encounter in practice are structured. And what you want to do is devise methods to learn that structure. For example, you might be a historian and you have a bunch of documents and you're interested in learning the underlying thematic structure for this collection of documents. Or you might be a political analyst and you want to analyze political speeches. Or you might be working at Netflix or Spotify and have a bunch of records of users listening to music or watching movies. And so what you want to do there is try to learn the underlying user preferences. Sometimes the structure is also temporal. For example, learning structure in language, in speech recognition, or you might have some medical data, which is like a set of records of patients visiting hospitals over time. And what you might be interested in is learn a low-dimensional representation of the patient so that you can do patient phenotyping or predict readmission to the hospital. The traditional family of models that we use usually to learn this structure is Bayesian hierarchical models. And I'll describe a specific family of Bayesian hierarchical models that encompass a lot of the models we encounter in practice. For example, you describe your model with a joint, and here you have the data. You have a set of global latent variables data that are shared across all the observations. You have sets of local latent variables, each latent variable being associated with one data point. And you write your joint as this decomposition prior over the global latent variable times the product of across the data points of conditional local latent given global latent variable times conditional of the observation given both the global and the latent variable. In this setting, finding structure is equivalent to performing posterior inference. What that means is I want to find the conditional distribution of the latents, both local and global, given the observations. And you have this ratio, joint over marginal likelihood, which we often cannot compute, so you have to resort to things like approximate inference, variational methods, or MCMC. And bottom line is that we have this family of models that give us an interpretable probabilistic structure. One very famous example of this family is latent Dirichlet allocation. You might be already familiar with it. If you are not, I will take some time to explain it. In LDA, what you have is a corpus of documents. So you have a bunch of documents. Remember our historian from the beginning. And what you do is you define a global set of k shared latent topics, beta k, each one being from a Dirichlet eta. Eta is a hyperparameter, usually fixed to induce sparsity. And then given those topics, what you do to generate a document is that you first draw from a Dirichlet to get a probability over the simplex. So theta will be your topic proportions, or the way in which the document you want to draw expresses the topics you defined earlier. And then given the sets of topics and the topic proportions, you generate each word in the document by first sampling an assignment, which is just a categorical over the proportions, and then you draw from the assigned topic, because remember the topic was a distribution over words as defined by the Dirichlet. So LDA has been applied to many applications and many domains in the digital humanities and political science and things like that. Here, I will describe an alternative to it that is more amenable to high dimensions. Because even though LDA enjoys something called conjugacy, meaning when the prior and the posterior belong to the same family, which makes inference very easy and tractable. So you could do something like coordinate ascent variation and inference. Although you have all those desired properties, it actually tends to fail when you have very large vocabularies. And I'll show results that actually show that. Another example, I put example in quote because people usually think about Bayesian hierarchical models when you have at least 2 levels of latency. In a deep latent Gaussian model, you have 1 level of latency. You have a local latent variable and the data. We have replaced the prior over the global latent variables with a neural network. By doing this, we can fit this deep latent Gaussian model within the Bayesian hierarchical framework. And it allows us to think what we trade off and what we gain or what we lose when we go from introducing this neural net over introducing a distribution over the global latent variable. Here, basically, you are replacing your inductive bias over the global latent variable with your choice of the architecture. I like to think of it like that because it then connects these 2 things together. You have the same decomposition of your joint. Now your joint is only over the observations and the local latent variables, because remember, now your global latent variables are actually deterministic. Those are parameters of the neural networks. You always condition on them. And then what you usually do is actually the conditional of the local given the global variables is just a standard Gaussian. And what you do to generate from this is you sample from the standard Gaussian, pass it through the neural network, and then get your parameters of your distribution. Say if it's a Gaussian, you'll get your mean and your covariance, and you get your observation like that. We forego conjugacy. We cannot use things like coordinate ascent variation or inference. And we also lost the interpretable probabilistic structure over our global latent variables. But we get expressivity when doing this. So there are trade-offs. I'll now talk about inference before moving on to describe a family of models that allow us to, like I said at the beginning, combine ideas from, say, probabilistic modeling, here hierarchical base, and also neural networks. So variational inference, you probably all are familiar with it. You're physicists. Mean field variational inference, I believe, originated from the physics literature. And what it consists of is that basically, remember, we wanted to learn our posterior over the latents. In variational inference, you define that via an optimization procedure. Here, I'm illustrating VI by putting myself in the setting where you have deterministic global variables. So theta here is fixed. I'm not doing posterior inference over theta. I'm only doing posterior inference over the local latent variable z. In variational inference, you basically approximate the posterior by first positing a family of parametric distributions. Here, parameterized by phi is the whole circle. And what we want to do, a circle is a variational family. Each member is q phi of z. What we want to do is find the variables phi that minimize some distance to the true posterior. Distance usually like the KL divergence. And the optimization procedure is simple. It's just start it, initialize it, and then move on to minimizing this KL up until you don't observe any more progress, so that you know that you have found the Q that is closest to the posterior. It turns out that it's intractable, so you cannot actually optimize it directly. But fortunately, when you write this KL divergence, you can decompose it as the difference between the log marginal likelihood of the data and a quantity called evidence lower bound. The log marginal likelihood doesn't depend on phi. So when you're doing posterior inference, minimizing this KL is equivalent to maximizing the elbow. And the elbow is this expected quantity. So expectation under your variational distribution of the log joint minus log variational distribution. It turns out that the first equality also tells us that by positivity of the KL, that the elbow is a lower bound of the log marginal likelihood of the data. So you can also optimize your parameters theta by maximizing this elbow. Amortized variational inference is a form of variational inference in the sense that is the same thing. What you just do is take your variational family and restrain it to be ones that are parameterized by a neural network. Each variational distribution is parameterized by a neural network that takes X as data and gives you the parameters of your distribution. Say if it's a Gaussian, you just pass X data through a neural net and get the mean and the covariance. And you still optimize the elbow. What amortized variational inference gives you is scalability, scales inference to large data sets, because we have a local latent variable for each data point. If you have a large data set, you will have to fit that many distribution. Amortized inference amortizes the cost of inference. So you go from one parameter for each latent distribution to a shared neural network that you have to learn. What my goal is in this talk is to describe a family of models that have interpretable probabilistic structure that deals well with high dimension and that you can do efficient inference with. By efficient inference, I simply mean what I talked about just now, amortized variational inference, because we want scalability. So there are 3 models that I have been developing. Some of them are already on arXiv, and one is still on the works, but will be on arXiv very soon. What they share in common is that they deal well with high dimension, and they do that by making a specific assumption on the likelihood. We will be working on the meaning space. I'll describe what that means. And we will be doing efficient inference with amortized variational inference. And we are enjoying the interpretable probabilistic structure of usual hierarchical Bayesian models. The first one is what we call the embedded topic model. It's a document model. It learns word embeddings and topics. And what ETM does, the embedded topic model, it has the same probabilistic structure as LDA. In that sense, it's interpretable. We know what's going on and how we generate data from it and what our inductive bias is when it comes to the data. And here's how it works. It defines a deterministic per word embedding matrix. I call it rho. So it's of dimension the vocabulary size times the dimension of the embeddings, vocabulary size, the number of words that I restrict myself to consider. And then we define also a shared global deterministic embedding matrix of what we want to discover. We posit this global deterministic matrix, and we want to learn what that is. It will turn out that these are topic embeddings, meaning we are embedding the topic in the same embedding space as our vocabulary. So you follow the same generative process as LDA. What it means is that for each document, you will draw your topic proportion. We don't care about conjugacy here. So instead of a Dirichlet, we will mimic what a Dirichlet does, which is non-negativity and constraining to the simplex. How we did that was you just sample from a Gaussian and then map that through a softmax. Now, to generate words in the document, you generate an assignment variable as before, but now you generate the word through this likelihood. What the likelihood says is that if I want to generate a word, I have to map it to the topic it is most similar to. In this likelihood, words that are similar together will be mapped to the same topic. That's what the dot product gives you. It's a measure of agreement. And the reason why this is desirable is that now you can deal with high dimensions. Suppose you have a very big vocabulary. You will have a better chance of having words that have the same meaning but that have different labels. It turns out that words that have the same meaning will have the same embedding. And so you will be able to map them to the same topic. If you also don't observe a word in the corpus, you don't need to observe that word specifically in the corpus. As long as you observe a word with the same meaning in the corpus, you will be able to deal with it. So what this gives us is we will be able to generalize better to unseen words. Often these are rare words too. And again, you can deal with high dimension. You will generalize better, all because of this simple construct of taking a per observation embedding with a global structured embedding, and then dot producting the two. It has the same interpretable structure as LDA, and we can fit it with amortized inference. What we did here to make inference efficient was, okay, you do amortized inference on theta, meaning you take a document, you represent it as a vector of dimension, the vocabulary size, where each entry in that vector is the number of times that word appears in the document, and then you pass that through a neural net, get your distribution, like mean, covariance, and then map to softmax to get a draw from the posterior over the topic proportions. But now for the discrete latent variable, the topic assignment Z, you could do variational inference on that and use things such as Gumbo softmax or the concrete distribution to get a low variance estimate of your elbow and do backprop, the usual procedure. But what we did here was just, we said, okay, we don't want to use approximations. Okay, you will have low variance, but they're still approximations at the end of the day. What we want is have a better approximation of the elbow. And we also have control over the number of topics, K. And so just marginalize out these discrete latent variables. That is an exact thing to do. It's not an approximation. So you do that, you have your elbow, backprop for it, use stochastic optimization. You get an efficient way of learning this model that enjoys everything we've talked about. Efficient inference, deals well with high dimension, and has an interpretable structure. To show you the benefits you get by doing this, we compare ETM with LDA on a control experiment where we pick a corpus, we build 5 different versions of it. Each version is the same corpus but with a different vocabulary, meaning it's the same corpus but we added way more words. Usually in topic models, people tend to prune words because you don't deal well with rare words or stop words. Here you don't have to worry about that. So we looked at how LDA and this new model behave under increased vocabulary, meaning as you add more and more words, rare or very frequent, how does your model deal with it? You are increasing dimension. What we saw was that LDA actually breaks as soon as the vocabulary starts increasing for this corpus. That might not be the case for all corpuses, but this is evidence that actually the original hierarchical Bayesian models that you have doesn't deal well with high dimension. That's not the case when you use that construct of working with the embeddings. We also looked at, say, comparing predictive power versus interpretability, not only LDA, but also for the ETM model that I just described. Here we considered another corpus, the New York Times, which is a way bigger data set. It has millions of documents, 1.8 if I recall. And the vocabulary size, we stretch it from 9,000 to up to 200K. This is the biggest vocabulary that I've seen for topic modeling in the literature. People usually don't stretch to that amount. But we can do this because of the simple, it's very simple when you think about it, but it has so much desired properties. You can go to this amount of vocabulary because of that. And what I'm showing here is basically a scatter plot of interpretability on the vertical axis and predictive power on the x-axis. The predictive power here is measured by document perplexity on document completion, meaning I give you a test set, a bunch of documents that you haven't seen before. Document completion, you pick each document in the test set, you cut it in half, determine your topic proportion on the first half, and then use that to predict the words in the second half of the document. So it's like a form of measuring strong generalization. So that's on the x-axis. On the y-axis, you have interpretability. The way we define it here is topic quality, which we defined as topic coherence times topic diversity. The reason why we didn't want to stop at topic coherence, as is usually done in the topic modeling literature, is because you might have the same topic which is perfect, but repeated multiple times. That's a failure mode that we wanted to get rid of, to not account for. So you have to multiply also by topic diversity. And topic diversity here is measured by taking just, you have your model, you learn your topics, and then you pick for each topic the top 25 words, and you count how many unique words you have in that topic. And you aggregate across all the number of topics.
Can I ask just quick, in terms of this, the word embedding part, you're learning that, but is there a reason that you, could you use like some off-the-shelf pre-trained word?
Yes.
Compare it with some like
Right, that's a great question, because this guy here, the labeled ETM, is the one where we use prefitted embeddings. And the ETM with parentheses LE is the one where we learn the embeddings. We wanted to showcase that you can actually do both. Yeah, the finding there was that the labeled one, where you use prefitted, tends to be more interpretable. Actually, maybe you can find that here. And the other one had more predictive power. So the plus sign is the one where you learn the embedding. Here, in this plot, bottom line is that the best document model would be the one on the top right, because it would be the one with higher predictive power and high interpretability. That's what we want. What you find here is that actually you get that with the ETM. You end up with NVDM, which is another document model that's not built on the probabilistic interpretable generative model of LDA. It just takes a neural net, remember the inference network that I described, to parameterize the variational distribution over the topic proportions. It just samples from that and then map it to a categorical. There's no, that's not what I described for LDA or this model. You can see that you lose in interpretability when doing that. So it has high predictive power, but highly not interpretable, which is not the case for ETM here, even when the vocabulary is as large as this. Any question on this result? What I'm showing here is actually the topic embeddings. Remember, we defined alpha, which is say, okay, each word has its latent low-dimensional representation. You define this topic in the same space. I'm showing those topics here, the topic embeddings here. You can see that it's granular. You have like a topic embedding around neighborhood, region, another one around roads and towns and bridges, another one on transportation, like car and train. So it does have structure, and it's managing to learn that. Here I'm just listing the embeddings. If you set your matrix row to be a free parameter that you also learn, it turns out you can learn good word embedding with this. And that's expected, because in here, skipgram, your context is just the surrounding words. You can think of this also as an embedding model, but where your context is the whole document. So it makes sense that it finds these interpretable word embeddings. Yes?
This is sort of a silly idea, but did you try doing like the word vector algebra with like the topics, so you could
right.
like, subtract out like a topic from a word? And then
Right. Yeah, I didn't do that word analogy, like king minus man, something. Yeah, I didn't do that. I'll try it just to see if it has that algebraic interpretation. Yeah, but it was interesting to see that you can both learn topics and embeddings and deal well with very large vocabularies. If there's no question, I'll move to a second instance. So the second one, we're dealing with temporality. So now our documents are moving over time. And what we do there is you follow the same procedure. The only thing that changes is now the likelihood. And because we want to measure how the topics vary over time, we also account for that in defining the topic embeddings, different from what we did before. So what we now do is we still define the deterministic per word embedding, row, free parameter, vocabulary size, and embedding size. But now you define your topic embedding, you put a random work over it, meaning that you condition on the previous topic embedding. And yes, and at each time step, that topic embedding is as before. It's a K times E matrix. because there are k of these topics. Now you follow the same generative process for each document. You draw your topic proportions, but now we account for temporality too in defining the topic proportion, because at each time steps now you have defined the topic. It's the same topic, but it's moving over time. And we accounted for that in defining the prior over the topic proportion. What we did was just use hierarchical prior there. So you place your random walk over some eta, and then you condition on that to draw the topic proportion. Now for each word, you have the same likelihood as for the ETM, meaning you sample an assignment and then just a categorical parameterized by the dot product. So this actually has the same probabilistic structure, the same generative process as dynamic LDA, except for the likelihood. And what that does, we already saw it, both for the ETM's construct, but also in the result that I saw before that. You can deal with very large vocabularies, and you can generalize better. So the way we did inference here was you still have to account for temporality. That's a bottleneck we have to deal with now. So that's also reflected in the inference procedure. What we did was do what's called structured amortized variational inference. So that latent variable theta d, you parameterize its posterior, its variational distribution, by an LSTM. The input to the LSTM at each time step is the aggregate of all the documents that appear at that time step. Remember, our data set is a corpus of documents, each assigned to a particular time step. So I aggregate all the documents that appear in a given time step, and I pass that through the LSTM to get the parameters of my variational distribution over the topic proportions. For the topic embedding, we just use mean field variational inference. There's nothing that prevents you from also using something that's more complicated. We prefer to be simple in that. So we use mean field for alpha. And yeah, you maximize the elbow like I described before. And it turns out that you manage to discover the underlying structure very well. For example, here I'm showing a topic about climate on the United Nations debates corpus. And in 1990, you can see that you went from discussing the ozone layer, which was the problem back then, to now discussing 2010 to 2015 global warming and gas emissions. We didn't have any information on this. I like this plot a lot because each of them, you can actually learn something from it. What I'm measuring here is, remember, each topic is across the whole, each topic, if I use softmax rho transpose alpha, I get a distribution V times T for each K. So what I did was just pick some words and track how they evolve over time. And that's what I'm showing here. I'm showing 8 topics. For each topic, I labeled the topic because I look at the words and see what they're about. So the labels on top are chosen by us. They're descriptive of the topic. And now I pick few words that were interesting on the topic and see how they evolve. If you look at the one, there's this topic on war that's like imperialism that were used before, which have now 0 probability. And then there's the topic on human rights, where you have gender inequality that in the 2010s have skyrocketed. Unfortunately, education remained very low. And you also have like climate change. That one was good. It's the one that I showed before. You have ozone, that peak is this one. You have this peak on the ozone and the waste, and then later in the 2010s, it's more about global warming and gas emissions. And yeah, and I picked this one. It was interesting too. You see the apartheid here. You see colonial from before. Now it's more talking about democracy and things like that. So it all makes sense according to our knowledge of history and what's going on over the world. And we were not told anything about this. We just discovered this by building a model that reflects our inductive bias. And we did that in a probabilistic way. If there are no questions, I'll move on to, am I going too fast?
No, it's fine.
Okay.
Can I just ask a minute? Can you just go back like to the slide where you had the models?
Yeah.
Like maybe, I think it's 2 more back.
2 more.
So maybe, so the LSTM, so where does the, seems like does the eta have to be generated, like is there like where does the LSTM fit into the generative model?
It's in the inference part. In the generative model, you have, it's already described here. In the inference part, you know you always, that same.
Yeah, it's not a recurrent prior.
It's a recurrent, it's a recurrent prior, because you're conditioning on the previous.
Yeah, but does not, the LSTM isn't imposing the prior, right?
The LSTM is imposing the variational distribution over eta. The variational distribution over theta is the same in the sense that once I give you eta, t, you will just draw from a Gaussian with that mean, and then map to softmax to get your topic distribution.
It could be like a more complicated, instead of the random walk, it could be like an LSTM recurrent prior too. Like it could be like looking back and doing some kind of fancy combination of what it's already generated.
Right. As in you can, well, I don't get.
Maybe we can talk about this.
You say you're defining this prior as an LSTM?
Yeah, well, you have like some more complicated parameterization.
Yeah, you can
like draw models, like draw.
Right, you can do that. Yeah, you can do fancier things.
But you're doing it in inference anyway, so
right.
That's the kind of like the important part.
Right. And what we did there, remember, is the LSTM is for eta, and then once I give you eta, you can draw from theta with that same log normal, logistic normal with mean eta. But yeah, you can certainly have a more complicated prior. Actually, the next model that I'll discuss is one where you also add expressivity in the generative process using neural networks. Not only in the inference part. Here we had this nice construct in the likelihood that was simple, but that was doing very well with high dimension. And we use efficiency and expressivity of the neural network in the inference part. The next thing that I'll discuss, we also use the neural net in the likelihood part. Those are called, okay, let me discuss it now. So this model, this is the one that's not on archive yet, but I'm very excited about it, because it falls under this whole thing that are called structured variational autoencoders. There are 2 main approaches in the literature. There's this thing, this paper that I like a lot by Matt Johnson, Ryan Adams, and I forgot the other author. I hope that's not bad. But it was basically defining, the same objective, combine hierarchical base with the expressivity of neural network. Not just for inference, but even in the model. And what they did there was you define, say, a mixture of Gaussian for your latent prior. Use the mixture of Gaussian, so you have discrete and you have your location latent variables, and then generate the likelihood by just passing that latent through a neural net. So the way they implemented their approach was through the prior. You make the prior as expressive as possible, and then use one neural network to get your observation. The other approach is similar to, has the same philosophy as what we are doing here, in the sense that they don't make the prior expressive, they make the likelihood expressive. And what they did was, you can call it basically a mixture of VAEs. You have, for each data point, you have to assign it to one of the VAEs. And their assignment mechanism was determined by a discriminator. What we did here was make that probabilistic, following the same thing I have been describing so far. So what we do is you define this per observation embedding. You can apply this to different data modalities, not just to text. I'm going to show results on images. You define this deterministic per observation embedding role, and then you now define K neural networks. each one with parameters gamma k. And then for each observation, you do the same thing, draw a proportion that will tell you what how this observation expresses along the different k-neural networks, expresses itself. And then for each element in your observation, you will draw an assignment from the categorical. Then now you draw a noise variable from standard Gaussian, pass that through a neural net. The output of that neural network has an implicit distribution. We don't put any assumption on that. Just take noise, pass it through a neural net. I call the output a landmark. It's related to vision. And then you take the dot product between that landmark and your per observation embedding to define your likelihood. Because one of our goals, remember at the beginning, was to be able to deal well with high dimension. This simple construct turns out to achieve very good performance in high dimension. And yeah, the output, you can be any exponential family, meaning that you can deal with real value data or categorical if it's text. And you can fit the whole thing with amortized variational inference. What we did was use the same approach. I marginalized out Z because we have, again, you can use these gumbo softmax or things like that, but I want to avoid approximations whenever I can. And here the reason why it's good to marginalize it out because you have control over K. So you can pick K reasonable enough such that this is not a burden to do. And then the noise variable, you do VI over it. So you have now two VI problems, 1 over theta and 1 over epsilon. And then you maximize your elbow. It turns out that you generalize better. And I showed over this before too. Here I'm showing generalization performance as measured by log likelihoods. So the higher the better. And I'm comparing to the two main approaches that exist right now, the structured VAE of Johnson et al. And the K-VAE, mixture of VAEs of Locatello et al. That one uses a VAE, but remember the assignment is through a discriminator. So you run actually into some instabilities with the approach of Locatello et al. Another problem that you run with from our side, from the approach of the Johnson et al. Model and from our model is that in the mixture of Gaussians case, when you defining your pi as a mixture of Gaussian and then passing that through a neural net to get your likelihood, you call some of the mixtures collapse. What they did in their model is to just place a sparsity inducing prior so that you can alleviate that a little bit. In our case, to prevent the experts from dying, we just did pre-training, which was also done in Locatello et al.'s paper. And it turns out that pre-training is a good solution to this dying expert problem that you run into when you do some sort of clustering with deep neural networks. And we controlled for the model complexity. So we made sure that every of these models have the same model capacity. Model capacity, by model I just mean model complexity, so same number of parameters. For the VAE, that's the only one that doesn't have. For the VAE and SVAE, you basically just scale up number of layers or the width of the layer to match the number of parameters of Lima and the Locatello model. And yeah, we tried 3 different benchmark data sets, and for all 3 of them, you can see that you get better log likelihood. And I attribute this to not inference or anything like that, but to this very simple thing. It might look trivial, but it's actually very, yeah, it's very, very good at like dealing with high dimension. If you have any question, any remaining question? Yes, go ahead.
Do the k-neural networks, do they assume like the categories of evidence?
Oh, yes, they specialize.
Yeah, it's like each of the
Yes, they specialize. Yeah, that can be interesting for people working in vision when you want to guide generation. Yeah, but the trade-off is that if you run into this dying experts issue, you're trying to alleviate it. So you do, let me pre-train. When you pre-train, you lose some of the specialization. So the experts, they, of course, focus on one particular like types of image. So if it's M, it's like particular types of digit, but they're also now generating some of the other digits. You don't have that if they don't die and you don't pre-train. They will each be like specialized.
Sorry, in this last model, you said there's these you have two elbows basically for the theta part and this one?
Yes.
So the loss is just the sum of the two?
Yeah, the usual elbow, yeah. Yeah.
But it's just the sum of the two?
Yes.
It's not a hierarchical elbow?
No, yeah. You could make it hierarchical, yeah.
Are there other questions? Were you raising a question? I have one more question. Is it in terms of this the document modeling, like in the end, originally you just have these like kind of abstract topics and things like that. So
right.
You're looking at like climate change, like someone is going through and somehow like looking at a bunch of examples and like giving them a label at that stage.
Right.
I'm just curious if there's a way. I mean, do people do something where to try to encourage the model to align the topics with what are already kind of recognized sets of topics?
That's interesting. What do you mean by that?
I'm just somehow, well, I'm not 100% sure, but I mean, maybe in the same way that you have like word embeddings and then you do these kinds of things, you could imagine that you took a bunch of topics, a bunch of articles that everyone agrees is they somehow label them as some topics.
Right.
I don't know, somehow some kind of pre-training and then encourage the topics to align in some sense, but I don't have something concrete in mind. But
alignment as in, I see. What do you mean by align?
I mean, it just seems like it's certainly possible that you could learn a topic that's like, if it was,
you mean
some linear combination of two different topics that appear a lot, and that have a similar language or something like that you might want to.
Right, you might have redundancy. If, for example, you will have that actually. If you choose a very large number of topics, and very large can sometimes just be 100, then some of them might actually overlap.
Right, or just to avoid the kind of labeling after the fact. Like if you already have a collection of documents that you've labeled, is it just to kind of automate the labeling of the learned topics? Yeah,
you can do that. Actually, I think people call that label. I think there's a name for that. But I thought that the beauty of all of this is that you don't have.
No, for sure. I'm just trying. Also, in terms of the interpretability part here, that like to the extent that when there is some physics knowledge, and in the sense you're also showing the plots that have specific topics, right?
Yes.
And like the reason that like the great plots with like apartheid and things like, you already know what that topic is about.
Right. Oh, I see what you mean.
Very tied up into the labeling.
Oh, right. So what you can do, I see what you mean now. What you can do to find the label is you can just map the embedding. You can probably find the embedding of the closest word because they're both now in the same embedding space.
Encourage that.
Right. Yes, you can do that, definitely. Yeah.
So there is like a literature on, I don't know if it's been revisited in the context of like newer neural plus topic stuff, but there is like in the traditional topic modeling literature, there's some literature on like anchoring or something where like they pick some representative word, and so like each topic has, like maybe you just pin the word climate. So you're not having that much prior knowledge. You're just saying something like, I want some topic that owns this word, and the other topics don't get any of it, or something like that. So
Right. Yeah, there's a whole theory about anchor words and topic models. We didn't study that, unfortunately, in both the DTM or the ETM, but you can certainly, look into something like that. If I remember correctly, it's like an anchor word belongs to only one topic. So you would avoid something like this overlapping thing. Yeah.
I have one more question unless someone else. Yeah.
I was going to say something related. So maybe I'm misunderstanding, but like if you basically had a set of embedded topics.
Right.
Like in the dynamic model, you like are sampling your alphas conditioned on the previous alpha here.
Yes.
So like if you could imagine. I'm not quite sure. I guess what I'm trying to say is something along the lines of like you take your embedding matrix and then you just kind of like sample deltas away from that.
Right.
So the prior like 0 is kind of like stick to the preset embeddings, but then like if you wanted to kind of like have it be different, you could like have some pay some k out to move on. Does this make sense?
You mean that row over there?
I mean
or the alpha?
The alphas.
You mean, so you advocate for changing the prior then?
Yeah, the idea is like parameterizing the prior with like basically a set of like a predetermined set of embeddings basically, and then just like you like are sampling deltas away from those.
But how will you find that we could prefit the word embeddings, but how would you find, say, oh, these are topic embeddings?
I'm just saying if you had if you had like a little library of topic embeddings or something, like if somebody
right.
was like here's a bunch, here's WordNet embedded, like these are topics, or like you take regular LDA.
Right, right.
Like,
or the ETM and then get the
ETM,
right.
And then just like say here's what this found, but like start with that, but then do your thing.
Yeah, you can do that. That would be like some sort of initialization.
Well, I was even thinking as like a prior, it's almost like you use that and then try to compute, like, we can talk about this later. Like
something
distance.
moving over time.
Yeah, you just pay some KL to move, like the further you want to move away from your little preset library, you like pay more KL.
But I feel like you already get that here without having to go through
this
the...
It's kind of like you're looking at history and you're moving away from, right? Like it's kind of like the same
I
idea.
see.
It's like instead of just moving away from what your previous topic, it's
right.
like also from a reference list of like
I see.
standard topics. That's,
right. Yeah, that would be cool. Yeah. Yeah.
I think that sort of captures like.
Right. Yeah, that's cool.
So I have, if I could, can you show the plot again with the versus time? I would think that for the audience here, that if we're thinking of this as like time dynamics and you don't know what all is going on, and you're able to somehow learn, like the topic equivalent would be somehow like maybe some coarse graining of the system.
Right.
And then these are the words are more like some detailed properties of what's going on for that. That if you start seeing time dynamics or something like that, that's would be super interesting. And I also wonder if there's a way where, like for instance, in the set of words that you're attaching, like to encourage it to find things that have this like interesting time structure, right? Like, because this somehow I don't know, maybe that's all. I guess it's maybe happening implicitly, but like you sort of learn the words that are important and see how they depend on time, and then you plot it.
Right.
Like it doesn't seem like you're like explicitly looking for something that maybe did evolve with time, or are you? Is that
we basically fit the model.
Right.
Now we get this topic matrix
right.
that's K times V times
right.
T. Then I'm visualizing it.
Right.
And then the way I'm visualizing it is I'm just picking the top, say, 20 for each. You have, say, 50 topics, you list all of them. And then I just looked at some that are interesting, that seem to be changing. Oh, now you assigned ozone at this particular time step. Later on, I look, it's now, say, global warming. I'll be like, okay, let me plot this evolution and see what
This seems like it would be very useful
yeah.
in the context that we've been talking about.
And the thing is that everything that I've described, if you are in the setting where you have something that they can think of as what you have for topic model, you can apply this. Say you have, I will call that composite data. So you have documents and words. If it's video, it will be, video and then sequence of images. You can apply these things. Yeah.
Okay. All right. Well, then we'll move to our lunchtime, and we're back. Our coffee break, and we're back on time. So yeah.